Hi, welcome to Sunil Maths tutorial, Galois Theory, class number 6. In this video, we start second topic of the first unit, adjunction of roots. Let us see the first definition, extension field. Suppose capital E and capital F both are fields and F is subfield. Capital F is subfield. Capital F is subfield of capital E. That's it. Then E is called extension field of F. Then E is called extension field of capital F. And we denote this by using the symbol. Capital E is extension of F. This symbol means E is extension of F. E is extension of F. Extension is nothing but subfield. So E is extension of F means this F is subfield. This F is subfield of capital E. That's it. And we denote this symbol. Remember that the symbol. It means E is extension of F and F is subfield of E. So right. Next, you remember that the fact, suppose E is an extension field. E is an extension field of F. E is an extension field of F. Then very clearly this E is called vector space over the field capital F. Very important point to remember. Capital E is extension of F. It means this E is vector space over the field capital F. So right. The next note point, very important note point. This is a symbol, dimension of E over F. This symbol represents the dimension of E over F. Dimension of E over F. So again, this is the symbol. Read it as dimension of E over F. Dimension of the field E over F. I think you know the definition of dimension. Dimension means the number of elements in the basis set of E over capital F. Very important definition. Again, it is also from vector space definition. See again, this symbol represents the dimension of E over F. And dimension means the number of elements in the basis set. Of field E over the field capital F. I think you know the definition of basis. In the vector spaces, we learned that basis is a subset of the vector space having two properties. The first one, it is linearly independent set, and second one, it spans the vector space. L of S is equals to vector space. Okay. Anyway, let us go for next note point and one of the important condition to remember here also. For example here R root 2 means this is the set of all elements which are in this form a plus b root 2 such that a comma b belongs to capital R. The basis of this set consists only two elements, 1 comma root 2. This is the basis for R root 2. So the dimension of R root 2 over the real numbers is equals to number of elements in this basis. We have two elements. So base is equals to 2. So okay, we see some more examples after next definition. Degree of E over F. Next definition, degree of E over F. Important. The degree of the field E over F is nothing but the dimension of E over F. The degree of the field E over capital F is nothing but dimension of the E over capital F. In another words, let capital E be an extension of F. Then the dimension of the field E, considered as a vector space over capital F, is called the degree of E. So to understand this definition, I write four examples here. Let us see one by one. The dimension of C, I mean the set of complex numbers over capital R, C of R. The basis of C of R is defined as set of all elements A plus IB, where A comma B belongs to capital R. Basis of C, basis of the vector space is 1 comma I. How many elements are there? 2 elements. So the dimension of C over R is equals to 2. Q power Q of 4 root 2 over Q. You can write this symbol like this. Q of 4 root 2 over Q. This symbol is wrong here. Q of 4 root 2 over Q. So here also Q of 4th root 2 is equals to A plus B 4th root 2. So the where A comma B belongs to Q. The dimension of this set is 1 comma 4th root 2. 1 comma 4th root 2. So dimension is 2 here. So the dimension is 2. And now see the dimension of Q root 2 over Q root 2 comma root 3. One of the again important definition, important example. Q of root 2 comma root 3. It is also a field. It is nothing but the set of all elements which are in this form. A plus B root 2 plus C root 3 plus D root 2 root 3 such that A comma B comma C comma D belongs to capital Q. The basis of this set is 1 comma root 2 comma root 3 comma root 2 into root 3. Now the dimension of this set Q of root 2 comma root 3 over Q, the dimension of this set is equals to the number of elements in this basis. We have 4 elements, so dimension is 4. Dimension is 4. Next, let us see C square of R. C square of R. Suppose C square of R be the vector space of all ordered pairs, not ordered pairs, of all ordered pairs. Of all ordered pairs of complex numbers over the field of real numbers. So the subset simply 1 comma 0, 0 comma 1 and I comma 0 and 0 comma I is the basis. This set is basis for the set C square of R. So dimension of this set is 4. So the dimension of C square of R over capital R is 4. That's it. So these 4 examples are important examples to understand the dimension of the field. Now we learn one very important theorem depends upon these extensions. So before going to that theorem, we see the finite extension. Finite extension, already we learned that here extension. Extension means that field is a superfield or subfield. Okay. Finite extension means if the dimension of the field E over F is less than infinity, the dimension of the field E over the field capital F is less than infinity, then we say that this E is called finite extension. This E is called finite extension of capital F. Finite extension of capital F. Otherwise, we say that infinite extension. Remember that this symbol, the dimension of E over F is less than infinity. Is less than infinity. Then we say that it is a finite extension. Capital E is finite extension of the field capital F. Now we are going to prove the very important theorem of field theory. Let us see the statement. This one. Let F subset are equivalent to E, subset are equivalent to K be fields. So they given that capital F is subset are equivalent to E, is subset are equivalent to K be the fields. And also they said that the dimension of K over E is less than infinity, and also the dimension of E over F is also less than infinity. Then there are 2 conditions. First condition is the dimension of K over F is less than infinity, and the second one, the dimension of K over F is equals to the dimension of K over E into the dimension of E over F. Both conditions are very, very important in field theory. Let us start one by one. Yes, they given that F is subset to E is subset to F is subset to E and E is subset to K, and dimension of K over E is less than infinity. Dimension of K over F is less than infinity. We have to prove that two conditions. The dimension of K over F is less than infinity. The dimension of K over F is equals to dimension of K over E into dimension of K over F. So right, let us start. Since the dimension of K over E is less than infinity, what it means? Capital K is finite extension. Capital K is finite extension of the field capital E. Capital K is finite extension means what it means? Capital K is finite extension means capital K is a finite dimensional vector space. Capital K is a finite dimensional vector space over the field capital E. Capital K is finite extension. It means it is a finite dimensional vector space over capital E. It means what it means? K is finite dimensional vector space means K has a finite basis. K has a finite basis over capital E. Let it be that finite extension would be that finite basis will be, let it be V1, V2, V3, and so on Vm. This is the finite basis of K over capital E, this point. So you can, from this is basis for, this set is basis for K over capital E. So now obviously you can write this one symbol. The dimension of K over E is equals to number of elements in the basis. So number of elements in the basis is M. So remember this point. Now next again you have to write that one. The dimension of E over F is less than infinity. Apply the same theory again. Apply the same theory what you said here. Apply the same theory here. Here also. What is this condition implies as? This condition implies as capital E is finite extension of F. Capital E is finite extension of F. Capital E is finite extension means capital E is finite dimensional vector space over capital F. Finite dimensional vector space over capital F. If it is finite dimensional vector space, then E has a finite basis. Then E has a finite basis over capital F. If it has a finite basis, let that finite basis be, let it be U1, U2, and so on Un. I mean this set is basis of E over capital F. If it is a basis, then dimension of E over F is equals to the number of elements in the basis is nothing but N. So now we form two bases for the vector spaces K and F. Yes, now we continue our proof. Now take an element U belongs to K. Let us take an element U belongs to K. If U belongs to K, and observe that capital K has a basis. Capital K has a basis with elements V1, V2, and so on Vm. we know that there is a property. Every element of the basis, every element of the vector space can be written as, every element of the vector space can be written as linear combination of elements of bases. This is very important point from vector spaces. Every element of the vector space can be written as a linear combination of elements of bases. Here u belongs to k and the bases are v1, v2 and so on vm. Then obviously this u can be written as linear combination of v1, v2 and so on vm. So I write like this. A1, there exist scalars A1 V1 plus A2 V2 plus and so on plus AM VM, which is equals to summation over I is equals to 1 to M AI VI, where these AIs are belongs to the field capital E, because K is a vector space over capital E. K is a vector space over capital E. Let it be equation number 1. Let it be equation number 1. So now again here this AI belongs to capital E and capital E has a basis. Capital E has a finite basis. What it is? I think it is U1, U2 and so on UN. Again apply the same property. Every element of the vector space can be written as linear combination of elements of basis. Therefore this AI can be written as linear combination of elements of U1, U2 and so on UN. U1, U2 and so on UN. That's it. So you can write this AI is equals to I'm sorry, I write 2 times. This AI is equals to BI1 U1 plus BI2 U2 plus and so on BIN UN. It can be written as summation over j is equals to 1 to n Bij Uj. Let it be equation number 2. Now using this equation 2 in equation 1, then what you get? U is equals to summation over I is equals to 1 to m, summation over j is equals to 1 to n Bij Uj into Vi. Now you clearly observe that the element u belongs to k, I mean the vector u belongs to k can be written as linear combination of elements of vi and vi and uj. What it means? This condition is nothing but u is the linear combination of elements of ui's and vi's. So now define a new set capital S is equals to having elements u1, u2, and so on un and v1, v2, and so on vm with the number of elements in S is equals to n into m. So there is a new set having all those elements containing all these ui's and vi's and their products also ui's into vj's. So from this we conclude that we define a new set S as not here, please, I conclude one more point here. To understand this set, you can write ui into uj into vi such that I is equals to 1 to and so on small m and j is equals to 1 to and so on small m. Don't write individual element, product elements. Don't write the individual element, product elements. So n of s is equals to, now it becomes n into m. So that is right. So it means from this we conclude that every element, every vector or every element u belongs to capital K can be written as can be written as linear combination of elements of S. Linear combination of elements of S. Therefore, K is equals to L of S. If K is equals to L of S, then obviously the dimension of K is equals to L of S. Then the dimension of K over F is equals to dimension of F. Dimension of F. Dimension of dimension of dimension of F, not F, dimension of K over F. Dimension of K over F. This is nothing but number of elements in S. Number of elements in S. Number of elements in S is n into m, which is finite. Which is finite. It means which is less than infinity. So the dimension of K over F is equals to n into m or m into n or m into n, which is less than infinity. It means which is less than infinity means the dimension of K over F is less than infinity means capital K is finite extension of F. Capital K is finite extension of capital F. This is the required first property. This is the required first property of our theorem. See the statement here. This is the required first property. Now we are going to prove that the dimension of K over F is equals to dimension of K over E into dimension of E over F. To prove this, suppose summation over I is equals to 1 to m, summation over j is equals to 1 to n, bij into uj vi is equals to 0, which implies it can be written as summation over I is equals to 1 to m capital I into vi is equals to 0. Let it be equation number 1, where I is equals to, capital I is equals to summation over j is equals to 1 to n bij into uj. This is nothing but summation over j is equals to 1 to n bij into uj. Now we are assume that suppose I is equals to 0. Suppose I is equals to 0. If I is equals to 0, then summation over j is equals to 1 to n bij into uj is equals to 0. What is uj here? Uj here means where u1 comma u2 comma and so on un, this is a basis for the vector space E over capital F. What is mean by basis? Basis is a linearly independent set. Basis is a linearly independent set. If it is linearly independent, then these vectors u1 comma u2 comma and so on un are linearly independent. If these vectors are linearly independent, obviously their coefficients bij is equals to 0. Their coefficients bij is equals to 0. If their coefficients bij is equals to 0, then equation 1 implies. Then this equation 1 implies summation over then equation 1 implies summation over I is equals to 1 to m ai, because bij is equals to ai into vi is equals to 0. Again here that vi's are v1 comma v2 comma and so on vm. This is a basis for k. Again every basis is linearly independent. These vectors are linearly independent vectors. If these vectors are linearly independent vectors, that scalars ai is equals to 0. Now we take that summation over j is equals to 1 to m, summation over I is equals to 1 to n, I is equals to 1 to m, bij uj vi is equals to 0 implies as all the scalars bij is equals to 0. It means in this linear combination all the scalars are equivalent to 0. If all the scalars are equivalent to 0, then the vectors uj into vi must be linearly independent. What it means? This this is nothing but capital S. We defined that this product of elements are lies in S. Therefore, S is linearly independent set. S is linearly independent. Already we proved that L of S is equals to K. L of S is equals to K. L of S is equals to K and S is linearly independent. Therefore, S is a basis. S is a basis for K over F. Remember that. S is a basis for K. Basis for the vector space K over capital F. Then the dimension of K over F. Then the dimension of K over F is equals to number of elements in basis. Number of elements in S. Number of elements in S is equals to m into n, where m is nothing but the dimension of K over E. N is nothing but the dimension of E over F. The first time here we show that K over E is equals to m and E over F is equals to n. So finally we show that therefore the dimension of K over F is equals to the dimension of K over E into the dimension of E over F. That's it. This completes the proof of the theorem. And remember this theorem also useful as properties of extension fields. Let us see the statement again and we conclude our proof. So suppose E subset to K be fields, and if K is dimension of K over E is less than infinity, dimension of E over F is less than infinity, then dimension of K over F is less than infinity and dimension of K over F is equals to dimension of K over E into dimension of E over F. This completes the proof of our theorem. Keep learning. Wish you all the best.